So I want to briefly introduce some activities of our Department of Measurement and our Laboratory of Magnetic Sensors. At the Department of Measurement, we work not only on sensor technology, but also on instrumentation, non-destructive testing, and other measuring systems and testing systems. So I will concentrate on our laboratory. You can find it easily on the web with more detailed information. We work with different types of technology, with anisotropic sensors, induction sensors, but our specialty are fluxgate sensors, and we apply these sensors not only to precisely measure AC and DC magnetic fields, but also for position sensing, speed sensing, electric current sensing, vibration monitoring, etc. And we also work on testing and measurements of magnetic properties of samples of matter, including paleomagnetic measurements. And there is a lot of applications, but today I will concentrate on space research. So this is not really space research. This is an application of our magnetometer with hanging under the drone for geophysical prospection, scanning of the vertical gradient of magnetic field. We are able to make precise 3D finite element simulations, not only of our devices, but for example, use computer-aided simulation for design of solar cell topology optimized for low magnetic field emission. We construct and test sensors. This is an example of 3-axial magnetometers using racetrack sensors. It's an X-ray image. This is a monitoring station for geomagnetic observatory. One of these instruments is installed in Budkov, which is owned by or maintained by Geophysical Institute of the Academy of Sciences, and a similar instrument is also in Greece. We developed a series of sensors and instruments, including Micro-fluxgate. The first aim was 20 years ago, but it never went into the production. It was, I would say, first prototype made by CMOS process. The last one was successful, and it's being produced by Texas Instruments. It's a fully MEMS integrated fluxgate together with the electronics on a single chip, and it's not purely our design, we were just participating on this. Why I'm speaking about these sensors, they are these these integrated flux gates, they have better properties than AMR sensors, and off-the-shelf AMR sensors are being used for nanosatellites. This is piece of history. Our magnetometer was on board Mimosa satellite. You remember Mimosa, it was not successful. The main instrument on board was micro-accelerometer, which failed, but our magnetometer on board was working successfully, so that's the heritage. I would say our own heritage we have. This is an example of this is a photograph of the sensor head, 3-axial fluxgate sensor head. Unfortunately, the sensor was not on the boom, it was inside the satellite, so even there was a magnetic cleanliness program. We measured mostly the magnetic field of the permanent magnets inside the satellite, etc. But the testing was successful. It was a kind of amateurish product. I remember the only space qualified element was memory. Otherwise, everything was made in industrial technology, industrial grade electronics, but it simply worked. We participated on several other projects. This is testing equipment which was developed together with Danish Space Research Institute for asteroid magnetometer, but it's a non-magnetic positioning platform which was used for calibration of magnetometers. Another cooperation, in fact, the historically first cooperation was on the development of magnetometer on board of Ørsted. Of course, it's almost 30 years ago. And then we also cooperated on the development of micro-accelerometer simulator and tester for swarm mission. We also worked on calibration. Well, we need, for the calibration of magnetometers, we need coil systems and shieldings. Regarding coil systems, it's important to calibrate the angular alignment and coefficient of the coils before we calibrate magnetometer. We are using, we developed algorithm which was successfully used for calibration of the coil systems we are using in Průhonice, close to Prague. Historically, that was developed by Geophysical Institute of Academy of Sciences, and now it's we have rented this facility which formerly belongs to the Botanical Institute. And this the calibration was repeated in Braunschweig, in 2 coil systems in Braunschweig, in fact, and now our dream is to repeat the same for the large testing facility in Goddard Space Flight Center, which belongs to NASA. We participated in not much with magnetic sensors, but more with general testing and sensor technology in large project which was called ISP-1, developing multiple use space propulsion systems. It was large consortium, and we made only a small piece of work, which included interesting topics like insertion of magnetic sensors inside the winding of cryogenic motors to be used for pumping the fuel. I mean, besides the practical results, we had also some publications out of that. You see the micro hole sensors inserted into between the winding of the electric motor, and some data collected and analyzed out of that. We developed not only scientific magnetometers, but also service standard magnetometers. As a result of one Toucher technical agency of the Czech Republic project, we developed a magnetometer together with CSRC company, now part of BD Sensors. And our specialty is the development of ultra-low noise fluxgate magnetometers. So what we aim is to get to push the noise below 1 picotesla at per square root hertz at 1 hertz, and we are being successful. In fact, my younger colleagues are working on two technologies, both based on advanced ferromagnetic materials with cooperation to Institute of Physics of the Czech Academy of Sciences and other institutions, Institute of Physics in Slovakia. And compared to existing devices, you see anisotropic magnetoresistors, tunneling magnetoresistors, and I would say off-the-shelf fluxgate, we are at better noise levels. This is one of the applications for monitoring of the Earth's variations. I do not want to go to the detail. Also, some exotic materials for future sensor technologies. This is an example of nanowire arrays. Yeah. Again, you see a lot of cooperation with Institute of Physics. This was measured on squid magnetometer at Cukrovarnická. This was measured on using microscope at Slovanka. And a lot of simulations. We also manufactured AMR magnetometer for very small satellites, which is less precise but much smaller, less energy consuming. And we also made specifications for radiation tolerance and for vibration tolerance of that instrument. And yeah, these are the latest results reducing noise, but noise is not the only parameter. Of course, there is a lot of other, sometimes even more important properties. And I think the last, this is the group. The last news is that we are a part of the new initiative, but we will hear more about it later this day. Thank you.